Welcome, Mr. Doman's Algebra 2 students. This is how we're going to solve nonlinear systems of equations. So let's say I'm rolling through my math world and I come across an equation or an opportunity to find out when I'm going to get the same values for x and y in two simultaneous equations. So I come across a problem that says solve the system of equations. We get it over here. I guess we could call it solve the simultaneous equations. Or I suppose I could say find the intersection. Or I guess I could say solve for x and y. And this should pique our remembrance because we spend a lot of time trying to solve systems of equations. Equations that have the same x value and the same y value in both of the equations at the same time. So we come across this, y and x, the relationship between the independent variable and the dependent variable, and its infinite relationship. So we have this equation that has an infinite amount of solutions, and we have this other one that also has an infinite amount of points, and we're going to try and find where they have the same values. All right, we had three methods. First one, we could solve by graphing. When we solve by graphing, we're going to graph both functions and find their intersection point. We solved by substitution. Solving by substitution, what we're going to do is we're going to find one of those variables in terms of the other, and then we're going to substitute it so that we only have one equation and one variable. And then the final bit was the elimination method, which uses a linear combination. The elimination method is a linear combination to cause one of the variables to eliminate, and remember we're going to need additive inverses. Okay, so let's examine all three methods and essentially when one is more useful than the other. So we can come across a bunch of different equations, right? We have the ability to graph. We don't know when we're going to do that. We might try substitution over here. Might want to substitute here. Elimination method. I could look at this one and I might want to use elimination because of these clues. Right, so these two problems are essentially what we're going to try, and we're going to make a decision on when to use these and how to use them. The first method, solving by graphing. Okay, I have two functions, f of x and g of x. Those two functions, I want to find out when they're equal. So because I have a calculator that will do the graphing for me, or I can use the software that's going to graph for me, I'm going to take that first function and set it in the first portion of the y equals, and I'm going to take that second function and I'm going to plug it into the second y. All right? Once I have it set up so that I can see my graph, I'm going to find the intersections. So I'm going to go over here and I'm going to find, hey, I have this graphing calculator and I'm going to plug in y equals x squared, and that gives me another function. I plug in the x plus 2 into the second, and I can notice that they give us the intersection points of -1, 1, and 2 and 4 as my solutions. So if I'm looking at this, I'm going to graph this, I'm going to graph that, and I'm going to find out where they intersect. My solutions would be x equals -2, and y equals +2. Or we could put it in the ordered pair, -2, +2. My other solution, the other intersection, you notice it crosses twice, which makes sense. This is a parabola, mirror image on both sides, so it's actually going to cross once, twice, is at 2. That was 1, 1. Well done. Sorry, notice my units are counting by 2, so this halfway point would have been 1. 1. This one is 1, 2, 1, 2, 3, 4. So my second solution set is going to be x equals positive 2, y equals positive 4, or more as an ordered pair 2, 4. And those are the two intersection points. Naturally, the intersection points are where they have the exact same value. So in this infinite set of values and this infinite set of values, there's only two specific points in which they have the exact same value. When x is negative 1, y is 1. When x is 2, y has to be 4. Solving by graphing is a preferable technique, especially when it's already set up that you have your function in standard form already, because you can put that function in the y1 and the y2 section. Solving by substitution. So wait a minute. If I have y1 and y2, if I'm looking at when they're simultaneous, what I can do is I can take the y2 part of it out, because I want to know when they're equal. I want to know when they have the same y value. So if y equals the first function and y equals the second function transitively, they equal each other. So what I can do is I can take this equation, and because they both equal y, and I want to know when they're both equal, I can take that equation and set it up so that the first equation equals the second equation. Squared. Perfect. So now I have an equation that's set up. If I look at this, I'll notice, yeah, I got two sides of the equation. There's some like terms on one side. What I can do is I can actually work to make this into standard form just by subtracting x. Subtracting 2 from the left side of the equation, and doing the exact same thing over here on the right. After some combinations of like terms, we notice we have our x squared minus 4 equaling 0. Squared. X minus x is 0, 2 minus 2 is 0, negative 2 minus 2 is negative 4. So now I have a quadratic equation that I can choose to solve any way I want. Because there are no linear terms, I'm going to go ahead and take the shortcut, and I'm going to solve using inverses. I'm going to use the additive inverse. To get x squared equaling positive 4. Inverse operation of squaring something is taking a square root, take a square root, add the plus or minus, so we get x equals plus or minus 2. Yeah. All right. So naturally, that is only going to be my x values, so I'm going to have to substitute those back in order to find the y values. So to me, I'm just going to pick whatever's the easiest possible to plug this in, and I'm going to go ahead and plug it into my linear equation. I'm going to plug in 2, going to plug in negative 2. 2 plus 2 is 4. And negative 2 plus 2 is 0. So when I'm labeling my intersection points, my first one is going to be 2, 4. And my next one is also going to be negative 2, 0. As my solutions. And those are my intersection points. I could double check that with the graph if I notice it's in y equals form, so I can't really argue that graphing would probably even be a better method in this case. But naturally, with solving by substitution, really all you need to do is isolate one of the variables and then substitute it into the other equation. That's going to take us from having two unknowns, which is unsolvable, and give us one unknown, which we can solve. The final method is going to be elimination. The elimination, what we're going to do is use a linear combination. A linear combination meaning I'm going to take this equation, I'm going to add it to this equation. Now, there's something that we need, there's something that we always need with a linear combination, is in order to do a linear combination that's going to cause elimination, we need this special thing called our additive inverses. We need additive inverses so that when we add things up, they're going to cancel out. So let's take a look at the equation at hand. Now, me being the guy I am, you'll notice I gave you an equation where x and negative x squared are already additive inverses. They're already additive inverses. So if I were to take these two equations and say combine them, I would end up with something that looks like this. Y plus y is going to be 2y equals, not plus, equals, x squared plus negative x squared is 0. Negative 2x plus 2x is 0. And 1 minus 1 is also 0. There's an equation. I can solve that equation. Divide both sides by 2, or recognize that y is going to be equal to 0 is one of my solutions. Okay? Now, to me, that's going to help out because now that I know my value for y, I can substitute that back in to either or both of my equations. And I can rewrite this as 0 equals x squared minus 2x. Minus 2x plus 1 squared. And then I could solve that however I want. I would transfer this right into intercept form using factoring x minus 1 times, x minus 1 equals 0, so my x values are positive 1 and then positive 1 again. Those are the basics. We're going to talk more about them when you get back.